today we're going to look at one of the tiny giants that powers our entire modern world, the Bipolar Junction Transistor, or BJT for short. It's in pretty much everything electronic, and we're going to peel back the layers, starting with the perfect, ideal theory, and then diving into the messy and honestly fascinating physics of how it really works. And you really don't have to look far to see just how important this thing is. The BJT wasn't just some small improvement. It was a total game changer. It's what kicked off the entire solid-state electronics revolution. Without it, well, the phone in your pocket, the computer on your desk, they just wouldn't be possible. So here's our game plan for today. We'll start with what a BJT actually is, then we'll get into its 4 different modes of operation. From there, we'll look at how it amplifies signals, figure out how to measure its efficiency, and finally, this is the really cool part, we'll see what happens when the perfect theory meets real-world physics. Okay, let's jump right in. At its core, what is a BJT? You know, the easiest way to think about it is like a tiny electronically controlled water valve. Except, of course, it's not controlling water, it's controlling the flow of electricity. And this is the magic trick right here. A BJT has 3 little legs: the emitter, the base, and the collector. You send a tiny little trickle of current into the base, and that acts like you're turning the handle on that valve. It opens the gate and allows a much, much bigger current to rush from the emitter through to the collector. The ability to control a huge flow with a tiny one, that's its superpower. But here's where it gets really clever. This isn't just a simple on or off valve. It actually has 4 completely distinct modes of operation. And understanding these modes is the key to using it for everything from amplifiers to digital switches. First up is what's called the forward active region. You can think of this as the BJT's main gig. It's the reason it's a star. In this mode, one of its internal junctions is turned on, while the other one is turned off. And it's this exact setup that allows that tiny base current to have incredibly precise proportional control over the huge collector current. This is the sweet spot, the mode you need for building amplifiers, for audio, for radio, for pretty much anything. Next up, we have saturation. Now this is like cranking that valve handle all the way open. Both junctions are now fully on, and the BJT just lets the maximum amount of current it can handle flow right through. It's basically acting like a closed switch. This is the perfect on state for all things digital. And of course, the opposite of saturation is cutoff. In this mode, both junctions are turned off. The valve is slammed shut. Practically no current can get through. This gives you your crystal clear off state, which is the other half of what you need for a digital switch. And just to be complete, there's a 4th mode, the inverse active region. This is basically what happens if you try to run the transistor backwards. It kind of works, but it's really, really inefficient. It's not used very often, but it does complete the picture of the 4 possible states. So we've established that the BJT's superpower is amplification. But how do we actually measure that? How do we put a number on just how powerful that little base current is? Well, we measure it with something called current gain, which you'll often see represented by the Greek letter beta. It's actually a really simple ratio. You just take the big current at the collector and divide it by the small current at the base. So if a transistor has a beta of, say, 100, that means for every 1 little bit of current you put into the base, you get 100 bits flowing through the collector. That's some serious leverage. But that brings up a really important question, right? If it's so good, why isn't the gain infinite? I mean, ideally, you'd want to use practically 0 current to control a massive flow. But we can't. So what's getting in the way? What are the real-world limits here? To get to the bottom of that, we have to talk about efficiency. If we go back to our water valve analogy, this is kind of like having leaks in your plumbing. There are 2 main ways that our control current gets lost or wasted, and that's what stops us from getting that perfect infinite gain. And these 2 culprits have names. One is the base transport factor, and the other is the emitter efficiency. Let's break down what those actually mean. So the base transport factor is really just a success rate. It's asking, what percentage of the electrons that leave the emitter actually make it all the way across the base to the collector? Because, you see, some of them get lost or recombined along the way. The higher this number, the more efficient the journey is. The emitter efficiency, though, this is often the bigger issue. This one measures how much current leaks the wrong way, backwards from the base into the emitter. Any current that goes backwards is just wasted effort. And in fact, this backwards leak is usually the single biggest thing that limits how much gain a BJT can have. Okay, so we've got the ideal BJT, and we've got the main things that limit its performance in theory. But now we get to the really juicy stuff, the part where our clean, simple model smacks right into the messy, complicated reality of physics. So let me ask you, does that perfect little electronic valve, one that behaves exactly the same way every single time, no matter what, does that actually exist in the real world? Yeah, you guessed it. Of course not. In reality, things get weird. There's a whole bunch of phenomena called second-order effects that start to show up, especially when you push the transistor with high voltages or high currents, and they change its behavior in really critical ways. First on our list is the early effect. What happens here is that as the voltage at the collector gets higher, it actually starts to squeeze the base region, making it physically narrower. Well, a narrower base means an easier trip for the electrons, so the collector current actually goes up a little bit, even if you didn't change the base current at all. It's like our valve starts to open itself a tiny bit more. Then you've got the Kirk effect. This one happens when you're blasting a ton of current through the device. The density of electrons gets so high that their own electrical charge literally pushes back and makes the base region wider. And a wider base slows the whole thing down and makes it less efficient. And it doesn't stop there. You've also got things like the Webster Effect, which describes how the travel time for electrons changes at high currents. Or current crowding, which is exactly what it sounds like. The current starts to bunch up at the edges instead of flowing evenly, and that can create dangerous little hotspots. So here's the big takeaway. The story of the BJT, and really all of modern electronics, isn't about some perfect, ideal component. It's a story about the constant battle engineers fight to understand, predict, and design around all these messy, complex physical realities, just so they can build devices that are both incredibly powerful and reliable. So think about this the next time you pick up your smartphone. Inside that little chip, there are billions of these transistors, and in every single one of them, at every single moment, this intricate dance between the ideal design and the messy laws of physics is playing out, all managed perfectly, just to make our digital world possible.